Greetings of the day to all of you and Eid Mubarak to all of you. Well, my dear students, over last 3 to 4 lectures, we have been discussing, effect or influence of various switching sequences on current ripple or stator flux ripple. And we have seen that certain bus clamping switching sequences or bus clamping PWM techniques, they give high THD or high stator flux ripple, whereas some other bus clamping PWM techniques or switching sequences, they give lowest stator flux ripple or lowest THD of the current. And we have seen how we can choose between various switching sequences in order to reduce the stator flux ripple or in order to reduce the distortion level in the current. Now, in today's lecture, which is probably the last lecture of this series, we are going to discuss how to reduce the harmonic torque, how to choose certain switching sequences in order to reduce the harmonic torques. Now, in our last lecture, we have already discussed how these harmonic torques are, produced in an induction motor, and how these harmonic torques result in torque pulsations or torque ripple. And now in today's lecture, we'll see how various switching sequences affect this torque ripple, or how do we design a PWM technique in order to reduce the torque ripple. So aim is not to reduce the THD of the current, aim is to reduce the torque ripple, which is one of the requirements in high power induction motor drives. Now, we have already discussed two types of PWM methods, broadly two categories of PWM techniques. One was low switching frequency PWM technique and another was high switching frequency PWM technique. In low switching frequency PWM technique, we discussed techniques like selective harmonic elimination technique, offline optimized PWM technique, or stored waveform PWM technique. And we have seen how we can choose pairs of switching angles in such a way that, or how we can choose switching angles in such a way so as to eliminate certain designated harmonics. And in high switching frequency PWM technique, we have studied various classes of PWM techniques, like we have discussed sine triangle PWM technique. We have discussed triangle comparison type PWM techniques, like various types of bus clamping PWM techniques, apart from third harmonic injection PWM techniques. We have also discussed advanced bus clamping techniques and so on. Now, the aim of using a pulse width modulation technique is now not to reduce the current ripple or not to lower the harmonic distortion in the current, but to eliminate certain harmonic ripples or harmonic torques, to eliminate certain harmonic torques and hence to reduce the torque ripple in induction motor drives. So we will start with low switching frequency PWM, and we will see how we can reduce the torque ripple using low switching frequency PWM, low switching frequency pulse width modulation PWM. You already remember we have discussed this low switching frequency PWM techniques in details, which was the first part in a series of lectures which constituted the first part of our discussions on PWM techniques. Actually, what we do, we have a switching plane. For example, we have a switching plane like this, switching angle plane like this. Along x-axis we have alpha 1 switching angle, and along y-axis we have switching angle alpha 2. Okay, we already know it. And I have already told you that the fundamental component of inverter output voltage is given by this equation, 1 minus 2 cos alpha 1 plus 2 cos alpha 2. We have already derived it in those lectures, in one of the earlier lectures. Let us assume this fundamental component of voltage is V1 star. This is the desired fundamental component of voltage. And let us assume we want to eliminate fifth harmonic component of voltage. Now, fifth harmonic component of voltage is given by this equation: 1 minus V5 is equal to 1 minus 2 cosine of phi alpha 1 plus 2 into cosine of phi alpha 2, and divided by 5, of course, and we want to make it equal to 0. And aim may be also to eliminate seventh harmonic component of voltage. So that is given by 1 minus 2 cosine of 7 alpha 1 plus 2 into cosine of 7 alpha 2 whole divided by 7. And we also want to eliminate this seventh harmonic component of voltage. Now, along the switching angle plane, so for example, this is our 0 degree. I say this is 0. This is 30 degrees, alpha 1 30 degrees, alpha 1 60 degrees, and alpha 1 90 degrees. And along this axis, we have alpha 2 30 degrees, then 60 degrees, then 90 degrees, like this. Now, it is something like this. This is our switching angle plane. And we have a straight line. Along this line, you can see alpha 1 is equal to alpha 2, because here alpha 1 is 30 degrees, alpha 2 is 30 degrees, 60, 60, 90, 90, and so on. This is a straight line which represents the condition alpha 1 equal to alpha 2. And it represents, so it's basically square wave mode of operation of inverter, we already know. And fundamental component of voltage will be 1 per unit. Okay, because inverter produces the maximum voltage when it is operating in square wave operation. And if you want to operate your inverter in square wave mode of operation, then alpha 1 has to be equal to alpha 2, and V1 will be 1 per unit, and this line alpha 1 equal to alpha 2, this contour, this gives square wave mode of operation of inverter. Fine. Then if you want V1, that is fundamental component of voltage, equal to say for example you for 0 fundamental component of voltage, this is the point, and alpha 1 equal to 60 degrees, and alpha 1 equal to 0 degree, and alpha 2 equal to 60 degrees gives V1 equal to 0, and alpha 1 equal to 60 degrees and alpha 2 equal to 90 degrees also gives V1 equal to 0. And then this is the contour of V1 equal to 0 per unit. Along this curve, okay, you have different combinations of switching angles alpha 1 and alpha 2, which will ensure V1 equal to 0. In a similar way, you can have another contour like this, which will give V1 equal to, say for example, 0.2 per unit. You can have another contour like this. This will give V1 equal to, say, 0.5 per unit. Another contour you may have like this. So these are constant, voltage contours. Here V1 may be equal to 0.8 per unit. So there are certain, solutions. When you solve these equations, we have seen that we may get a unique solution. We may get, multiple solutions. Say, for example, you want V1 equal to 0.7 per unit. For V1 equal to 0.7 per unit and V5 equal to 0, using this switching angle plane, you can have either a unique solution or you can have multiple solutions, that is different values of alpha 1 and alpha 2, which will give V1 equal to, say, 0.7 per unit and V5 equal to 0, or you may not have any solution at all. For example, for V1 equal to 0.98 per unit to 1 per unit, we may not have any solution at all. Okay, the switching angles are like this, as we already know. This is our, omega t, and something like this. Our pole voltage, say pole voltage VRO, will be something like this. So this is angle, alpha 1, switching angle alpha 1. This is switching angle alpha 2. and this is 90 degrees. So this is the pole voltage. It is plus VDC by 2, and it is here minus VDC by 2. So here we go from minus VDC by 2 to plus VDC by 2. At switching angle alpha 1, the transition takes place from plus VDC by 2 to minus VDC by 2 because the bottom switch of inverter will be on. And at switching angle alpha 2, the top switch turns on. So there is transition of pole voltage from minus VDC by 2 to plus VDC by 2. So there are two switching angles per quarter. For example, we have two switching angles per quarter of waveform. So this will give V1 equal to V1 star and V5 equal to 0. Okay. And if you want V7 also equal to 0, then you will have three switching angles. You will have alpha 3 also. Okay. And then in that case, V7 will also be equal to 0. Fine. Now, we have already studied in details that if you want V1 equal to V1 star, V5 equal to 0 and V7 equal to 0, we know what are the curves which give V5 equal to 0 and what are the curves which give V7 equal to 0. For example, if you remember in one of the earlier classes, this was the contour. This was V5 equal to 0 curve. V5 equal to 0. So along this contour, different combinations of alpha 1 and alpha 2 will be there, which will give V5 equal to 0. Okay, and then intersection of these contours, constant, fundamental voltage contours, with this will give a desired value of fundamental component of voltage. For example, if your requirement is that fundamental component of voltage should be 0.8 per unit and V5 should be equal to 0, then this is the V1 equal to 0.8 per unit line. It intersects with V5 equal to 0 curve here. So this is the point at which V5 will be equal to 0 and V1 will be equal to 0.8 per unit. Okay, so depending upon what is the fundamental voltage requirement, so you can have different switching angle combinations which will give you V1 equal to V1 star and V5 equal to 0. Now if you want V7 equal to 0, then you may have solutions. V7 equal to 0 curve will be something like this. Excuse me. It will be something like this. So this curve is V7 equal to 0 curve. And V7 equal to 0 curve is this also, although this is not our area of interest. And V5 equal to 0 curve is this. This is V5 equal to 0 curve, and this is V7 equal to 0. We have already discussed it in one of the earlier classes. We have got all these contours, V5 equal to 0 contours like this and like this, V7 equal to 0 contours like this, this and this. We have done it in details. Okay. Now, accordingly, for example, V5 equal to 0 may be your requirement, or V7 equal to 0 may be your requirement. So accordingly, this is how you get it. Okay, so fine. So this is, selective harmonic elimination. Now our aim is not to eliminate harmonics. Our aim is to eliminate harmonic torques. Let us see how we can use this selective harmonic elimination or low switching frequency PWM technique for elimination of harmonic torques. I will write here selective elimination of harmonic torques. Selective elimination of harmonic torques. This is the requirement now. Okay, I will draw the switching angle plane for your reference again. This is alpha 1 axis. This is alpha 2 axis. This is alpha 1 equal to 30 degrees, then 60 degrees, then 90 degrees. Alpha 1 cannot be more than 90 degrees. We already know that. Similarly, alpha 2 30 degrees, 60 degrees, 90 degrees. Alpha 2 can also not be more than 90 degrees. That's also known to us. And this is what we get. And another requirement is that alpha 1 should be less than alpha 2. So this upper triangle is our area of interest. Okay. Now, our aim is not selective elimination of harmonics in the voltages, but our aim is selective elimination of harmonic torques, which are troublesome in induction motor drives, especially in high power induction motor drives. And we already know, if you remember, let us suppose our aim is to make T6 equal to 0. So sixth harmonic torque equal to 0. We already know, we have studied in and we have seen in last class that the sixth harmonic torque is proportional to, it is basically produced by the interaction of fundamental flux on stator side and say fifth harmonic current on the rotor side. Okay, I told you that the harmonic torques are because of interaction of stator fundamental flux and rotor harmonic currents. Stator fundamental flux is phi1, say rotor side harmonic current is, you can take fifth harmonic component of current. So interaction of phi1 and I5 produces sixth harmonic torque. Because we already know phi1 is the fundamental flux, and this fundamental flux, this psi1, rotates at speed of omega in counterclockwise direction. This is the stator flux. And in the rotor you have fifth harmonic component of current that also results in a revolving magnetic field, and that revolving magnetic field you can call that psi5, that is rotating at a speed of 5 omega but in opposite direction, because phase sequence for fifth harmonic current is opposite to fundamental phase sequence. Okay, so what is the relative speed between the two? It is omega plus 5 omega, that's 6 omega. And 6 omega means the interaction of phi1 and phi5 will give rise to a harmonic torque T6, which will be revolving at a speed of, with a relative speed of 6 omega. So this is the production of sixth harmonic torque. We also know that sixth harmonic torque is also produced by interaction of fundamental flux and seventh harmonic component of current. Okay, now fundamental flux is rotating in counterclockwise direction at a speed of omega. Seventh harmonic current in the rotor gives rise to seventh harmonic revolved magnetic field, which is rotating at a speed of 7 omega in the same direction as fundamental flux, because phase sequence remains same. So what is the relative speed between the two? Which is 7 omega minus omega, that is again 6 omega. So this also gives rise to sixth harmonic torque. That's what I have written here. Now our aim is to make T6 equal to 0. So T6 can be made equal to 0 if we make, say for example, T6 is proportional to I5 minus I7 and equal to 0. We want to make T6 equal to 0. We can make T6, that's sixth harmonic torque, equal to 0 if this difference between fifth harmonic rotor current and seventh harmonic rotor current, if I5 minus I7 we are able to make equal to 0. Now we know that fifth harmonic current is proportional to V5 by 5, fifth harmonic voltage divided by harmonic order 5, and seventh harmonic current is also proportional to V7 by 7. That's already known to us, we know it. So therefore T6 will be proportional to, in terms of voltage, instead of writing I5, I can write V5 by 5 minus I7, I can write V7 by 7. So this equation tells us that if we make the difference between these two voltages, V5 by 5 minus V7 by 7, if this difference between the two voltages is made equal to 0, we choose V5 and V7, that is fifth harmonic voltage and seventh harmonic voltage, in such a way that V5 by 5 minus V7 by 7 is equal to 0. That means if we choose V5 and V7 such that V5 by 5 minus V7 by 7 is equal to 0, that will make sixth harmonic torque equal to 0. Very simple. So therefore, for selective for selective elimination of harmonic torque, say for selective elimination of sixth harmonic torque, the equation will be V1 equal to 1 minus 2 cos alpha 1 plus 2 cos alpha 2 equal to V1 star. So you have to use, the selective elimination of harmonic torque, this low switching frequency PWM in such a way. First of all, you have to set fundamental component of inverter output voltage equal to desired value using this equation. And then your another equation will be T6 sixth harmonic torque proportional to V5 by 5 minus V7 by 7, and this sixth harmonic torque you have to make equal to 0. So you have two equations. Solve the two equations, and using, these are both numerical, equations, transcendental equations. You have to solve them using numerical technique, iterative procedure, in such a way that finally you get the solutions with V5 by 5 minus V7 by 7 equal to 0. That will make T6 equal to 0. Now, if you want T12 also to be equal to 0, so you will have another equation. If you want T18 also equal to 0, you will have more switching angles. If you want to make T6 equal to 0, then you will have only two switching angles, alpha 1 and alpha 2. For example, you have two equations and two unknowns. These are two equations and unknowns are two switching angles. You can solve them using iterative numerical techniques like Ranga-Kutta technique or any other, say, Newton-Raphson technique. Find alpha 1 and alpha 2 switching combination, store that in lookup table, retrieve alpha 1 and alpha 2, and fire your inverter in such a way that you get your objective is fulfilled. V1 is equal to V1 star and T6 is equal to 0. If you want T12 also equal to 0, then you will have another switching angle, alpha 3, and you will have another equation. So you will have three equations and three unknowns. If you want T18 also equal to 0, so more equations. T24 also equal to 0, more equations. Solve them using iterative procedures and get the desired results. Now let us focus here on this objective, that V1 equal to V1 star and T6 equal to 0. So you need only two switching angles, alpha 1 and alpha 2. So you have two unknowns, two equations, solve them, you'll get the desired result. And we already know, if you want to make, your fifth harmonic component of voltage is V5 equal to 1 minus 2 cosine of 5 alpha 1 plus 2 cos of 5 alpha 2. If you want this equal to 0, and you want V7 also, which is, of course, this is divided by 5. This is 1 minus 2 cos of 7 alpha 1 plus 2 cos of 7 alpha 2 whole divided by 7 equal to 0. Okay, if you solve them, you will get the contour for V5 equal to 0. For example, just few minutes back, I have already discussed it with you. You will get something like this. This is the contour for V5 equal to 0. Another contour will be somewhere here. This is also V5 equal to 0 curve. Now, if you want V7 also equal to 0, so you will get these contours, like you will get a contour like this. This is for V7 equal to 0. You will get another contour like this. This is also V7 equal to 0. You will get another contour or curve like this. This also represents V7 equal to 0. Fine. Now, you have to choose those points where V5 by 5 minus V7 by 7 equal to 0. One of the points is this, where these two curves intersect with each other. V5 equal to 0. For example, here you can see V5 is equal to 0, but V7 is not equal to 0. So V5 by 5 minus V7 by 7 will not be equal to 0. This is the point where V5 equal to 0 curve and V7 equal to 0 curve, they intersect with each other. And at this point, you can see V5 is equal to 0 as well as V7 is equal to 0. So V5 by 5 minus V7 by 7 at this point will be equal to 0. And in the vicinity of this point, like I will show by dotted line like this, in the vicinity of this point, along these dotted lines, you may not get V5 by 5 equal to 0. You may also not get V7 by 7 equal to 0, but their difference you can find is equal to 0. That is in the vicinity of these points. Similarly, these V7 equal to 0 curve and V5 equal to 0 curve, they intersect here also. So here also you can see V5 is equal to 0, V7 is equal to 0, and in the vicinity also you can find V5 equal to V5 by 5 minus V7 by 7 equal to 0. Another point of intersection is this. Here also you can find V5 equal to 0, V7 equal to 0, and in the vicinity you can find there are certain points where certain solutions where V5 by 5 minus V7 by 7 equal to 0. But the problem with this and this is that we know that this represents V1 equal to 0 per unit. We would never like to have V1 equal to 0. We would like to have inverter output voltage equal to V1 star, depending upon induction motor voltage requirements. So therefore, these two solutions will not pursue. So we will pursue this solution, because at this solution, V1 will not be equal to 0. V1 will be having some, say, some value, some positive value like this. It may be 0.7, 0.8 per unit, and simultaneously you can see at this point and in the vicinity of this point, you will get V5 by 5 minus V7 by 7 equal to 0. Okay, so therefore this is how we solve these equations. We can make let alpha 1 equal to 0, and you can find alpha 2, I mean different for T6 equal to 0, the same way as we have done when we were discussing elimination of certain selective harmonics. Here we don't want to eliminate harmonics, we want to eliminate harmonic torques, and we don't want V5 equal to 0 and V7 equal to 0. We want this difference, V5 by 5 minus V7 by 7 equal to 0, and this dotted line will give us those solutions. Okay, so therefore you can use, we have these equations, two equations, we have two unknowns, we solve them using numerical iterative procedures, and we get different combinations of alpha 1 and alpha 2 for which this relation, this equation is fulfilled. That is V5 by 5 minus V7 by 7 equal to 0, and V1 will be equal to V1 star. So that will make V1 equal to V1 star and T6 equal to 0. So it will eliminate sixth harmonic torque. So therefore harmonics are eliminated in pairs to eliminate a particular harmonic torque. Okay, like V5 and V7, this pair, the difference between them is made equal to 0 to eliminate a particular harmonic torque, T6. Make T6 equal to 0. Similarly, if you have to eliminate 12th harmonic torque also, or 18th harmonic torque also, so you will have more equations and you have to solve them. So you will get, instead of switching angle plane, you will get spaces, three-dimensional spaces, 3D spaces, and there you have to solve for, say, alpha 1, alpha 2, alpha 3, alpha 4 in such a way that the difference between the voltages is 0, and V5 by 5 minus V7 by 7 equal to 0 for elimination of T6. Similarly, Vx, say for example Vx by x minus Vy by y equal to 0 for eliminating some other harmonic torque. So this is how we can use low switching frequency PWM for selective elimination of harmonic torques. Fine. Those of you who are interested in studying this at their research levels, in their MTech projects or dissertations, you can download very good journal publications, conference publications, transaction publications, and you can study those, and you can see how this harmonic elimination of how the selective elimination of harmonic torques is achieved. Okay, and you can then design a simulation model, and you can go for selective elimination of certain harmonic torques. Right. So this was about how we can use low switching frequency PWM for elimination of harmonic torques. What about high switching frequency PWM techniques, which we have been studying over the last many lectures? How can we use them for elimination of harmonic torques? We are going to discuss briefly now that is high switching frequency PWM. High switching frequency PWM techniques. When I say high switching frequency PWM techniques, it means sine triangle modulation. Let us take three-phase voltage source inverters, sine triangle PWM. It means, triangle comparison PWM, triangle comparison PWM, where the modulating wave is not sinusoidal wave, but it is, non-sinusoidal wave, depending upon the injection of common mode signal. For example, this can be divided into third harmonic injection PWM, and this can also be divided into bus clamping PWM, bus clamping or discontinuous PWM techniques, discontinuous PWM, and advanced bus clamping techniques using space vector approach, because we already know advanced bus clamping techniques are possible only through space vector approach, not through triangle comparison approach. Advanced bus clamping PWM. So these are various types of high frequency PWM techniques which we have been exclusively studying over last many lectures. So these are all the categories of high switching frequency PWM. Now when I say high switching frequency PWM, so we will not have fifth harmonic, we will not have seventh harmonic, we will not have 11th, 13th harmonic. There will be no lower order harmonics. There will be harmonics are shifted at high switching frequency, around switching frequency and its sidebands, 2 times switching frequency and its sidebands, and so on. So therefore, the harmonic torques at lower, harmonics, which are created by lower harmonics, will not be there. There will be harmonic torques which are produced by, higher order harmonics around switching frequencies and multiples of switching frequencies, and we want to eliminate those harmonic torques. Okay. Now, in order to eliminate those harmonic torques, we have studied various types of PWM, techniques like space vector PWM techniques, various types of switching sequences we have already studied. We have studied, if you take switching sequences, which we have already studied in last 3 to 4 lectures. We have a conventional switching sequence. Conventional switching sequence, that is 0127-7210. This is one subcycle, this is another subcycle. We have already studied it. And then we have bus clamping sequence, or yes, I should write bus clamping sequences, switching sequences like 012-210. Here only null vector 0 is used for time tz, null vector 7 is not used, and 721-127. Here only null vector 7 is used in both the subcycles. So these are bus clamping sequences. This bus clamping sequence will result in clamping of each phase leg to negative DC bus. This bus clamping sequence will result in clamping of each phase leg to positive DC bus. And when you use both of them, like in 60-degree clamp PWM or 30-degree clamp PWM, they will result in clamping of each phase leg for equal interval of times to positive DC bus and negative DC bus. Maybe in a continuous way, in continual clamp PWM, or in a split way, in split clamp PWM. We have already studied those. I'm not going into those details. Already we have discussed those clamping sequence and those bus clamping PWM techniques in details. And then there are advanced bus clamping PWM techniques, advanced bus clamping sequences, which are also called double switching clamping sequences. Double switching clamping sequences. We have studied those also, like 0121, 1210. Here, active vector 1 is used twice. It results in, switching of one phase leg once, switching of another phase leg twice, and clamping of another phase leg to negative DC bus. Okay, and 7212-2127. This will again result in switching of one phase once, another phase will be switched twice, and another third phase will be clamped to positive DC bus. Okay, and then based on this we have studied different types of advanced bus clamping techniques like 60-degree clamp, 30-degree clamp, and so on. And we have another type of bus clamping, advanced bus clamping sequence, which we have not earlier studied. That may be 1012. Okay, so that is 1012 dash 2101. 1012-2101. So we have one advanced bus clamping sequence like this 0121 1210. I can bring this one here, so 1012 and then 2101. This is also a double switching clamping sequence or advanced bus clamping sequence. And another is, see, we have 7212. I bring this 2 first, so 2712 and 2172. These are also double switching clamping sequences. We have studied these double switching clamping sequences earlier, previously. We have not studied these double switching clamping sequences. These are also types of double switching clamping sequences or advanced bus clamping sequences. So out of these, this is double switching clamping sequence. These are also double switching clamping sequences. From torque ripple reduction point of view, these double switching clamping sequences or advanced bus clamping sequences are very important. I mean, they result in more reduction or more reduced torque ripples. So let me briefly discuss with you these double switching clamping sequences, which we have not earlier studied. I will briefly discuss with you. So I will write here a double switching clamping sequence or advanced bus clamping sequence. Let me discuss first this 1012-2101. Okay, so it is something like this. Let us consider sector 1 of our space vector PWM. This is null vector 0 with switching sequence minus minus minus. This is null vector 7 with switching sequence plus plus plus. This is active vector 1 with switching sequence plus minus minus. This is active vector 2 with switching sequence plus plus minus. This is in sector 1, and time averaging of these will give rise to rotating reference vector Vref, and we already know that this Vref into Ts is equal to V1 T1 plus V2 T2 plus Vz Tz. So this is the volt second balance. Vref Ts is the subcycle duration, is the volt second of reference rotating vector. And V1 T1 plus when we apply null vectors and active space vectors, so this is the total volt second. This application of null vector 0, null vector 7 and active vector 1, active vector 2 and time averaging them will give rise to volt seconds, which should be equal to this reference volt second balance. That is called volt second balance. So therefore, by time averaging of this null vector and these active vectors will produce a reference voltage vector which is very close to this Vref. Okay. However, we know that when a particular instant, when a particular space vector is applied, says null vector 0 or active vector 1 or active vector 2, there is always an error voltage vector. That is always an error between what is desired and what we apply, and that results in stator flux ripple. We have already studied that, and that stator flux ripple results in distortion in the line current. And we will very soon in today's lecture study that the stator flux Q component of stator flux ripple is responsible for torque, production of torque pulsations or torque ripples or harmonic torques. Anyway, so this is I would like to study this or discuss with you this double switching clamping sequence or advanced bus clamping sequence 1012-2101, which we have not studied earlier. So we start with 1. I mean, we start with active vector 1. We are at active vector. Active vector 1 is applied for time interval T1 by 2. because this active vector 1 is applied twice. So total time interval for active vector 1 is t1, so we divide it into t1 by 2 each. So active vector 1 is applied across the load for time interval t1 by 2, then null vector 0 is applied. So we move from active vector 1 to null vector 0. It is applied for time interval tz, full time interval tz. Okay, then active vector 1 is again applied. So we move in this direction. It is applied again for time interval t1 by 2. Then active vector 2 is applied. Active vector 2 is applied for time interval t2. So that completes subcycle. In another subcycle, active vector 2 is first applied for time interval t2 dash. Then active vector 1 is applied. So we move from 2 to 1. It's applied for time interval t1 dash by 2. Then active vector 0 is applied. So we move from 1 to 0. It's applied for time interval tz. Then active vector 1 is, after applying null vector 0 for time interval tz dash, active vector 1 is again applied. So we move from 0 to 1 and active vector 1 is applied for time interval t1 dash by 2. So you can very clearly see that, when we move from 0 to 1 or 1 to 0, which phase switches. R phase is 0 here. It has a status of minus here, plus here. So R phase switches. And it switches twice. And when we move from active vector 1 to active vector 2 or 2 to 1, Y phase switches, because Y phase has a status of minus here and plus here. So Y phase switches. Since we are not using null vector 7, we are using null vector 0 only. So B phase does not switch at all. So therefore B phase is clamped to negative DC bus. You can see B is minus here, minus here, minus here. So B phase is clamped to negative DC bus, B minus. So therefore R phase switches twice, Y phase switches only once, and B phase is clamped to negative DC bus. So this is for advanced bus clamping sequence 1012. Okay. What about advanced bus clamping sequence 2712? I will write here. Double switching clamping sequence or advanced bus clamping sequence 2712 2172. Okay, let us study this. We'll again take sector 1. This is null vector 0. This is null vector 7 with switching sequence plus plus plus. Active vector 1 plus minus minus. Active vector 2 plus plus minus. Time averaging of null vector and active vectors synthesizes the rotating reference vector Vref. This is spatial angle alpha. Vref is at an angle alpha. And now our clamping sequence is like this. We start with active vector 2. So active vector 2 is applied for time interval t2 by 2 because 2 is applied twice. So active vector 2 is applied for time interval t2 by 2. And then null vector 7 is applied. So we move from 2 to 7. Null vector 7 is applied for full time interval tz because null vector 0 is not applied at all. Then active vector 1 is applied. Okay. Active vector 1 is applied. 27. Sorry, it is 2721. I'm sorry, it's not 2712. It is 2721 and 1272. Right. So 2 to 7, then again 2 back to. That means active vector 2 is again applied for same time interval t2 by 2. And then active vector 1 is applied for time interval t1. So we move from 2 to 1. That completes subcycle. In another subcycle, active vector 1 is first applied for time interval t1 dash. Then active vector 2 is applied. So we move from 1 to 2. It's applied for time interval t2 dash by 2. Then null vector 7 is applied. We move from 2 to 7. Null vector 7 is applied for time interval tz dash. Then active vector 2 is again applied. We move from 7 to 2. It's 2 is applied for time interval t2 dash by 2. That's all. That completes the second subcycle. Now we can see when we move from 2 to 7 or 7 to 2, which phase switches. B is plus here, B is minus here. So B phase switches and it switches twice like this. And when we move from 2 to 1 or 1 to 2, Y phase switches because Y is plus here, Y is minus here. So Y phase switches. And which phase does not switch? R phase does not switch at all. R is plus here, plus plus, so R phase is clamped to positive DC bus. So therefore, using this advanced bus clamping switching sequence 2721-1272, it results in switching of B phase twice, switching of Y phase once, and clamping of R phase to positive DC bus. So that was about, double switching sequence 2721, or advanced bus clamping sequence 2721-1272. Fine. Now these two switching sequences, advanced bus clamping sequences, are applied to give advanced bus clamping PWM scheme like this. So we will have advanced bus clamping PWM scheme. Like we will have 60-degree clamp PWM. It can give rise to 60-degree clamp PWM like this. So let me draw the space vector diagram. This is active vector 1. This is active vector 2. This is active vector 3. This is active vector 3. This is active vector 4. Active vector 5. Minus, minus, plus. And active vector 6. Plus, minus, plus. Then we have two null vectors, 0 and 7. Our rotating reference vector will be rotating in a circular path. Okay. This is our sector 1. This is sector 2. This is sector 3. This is sector 4. This is sector 5. This is sector 6. And I will bifurcate each sector equally into two equal parts, 30 degrees each, as we have been doing in other bus clamping sequences also. So fine. We can start with sector 1, and of course we can start with switching sequence 1 0 1 2 2 1 0 1. Active vector 1, then null vector 0, then 1 again, then 2. Double switching clamping sequence, or advanced bus clamping sequence. Then 2 first, and then 7. 2 7 2 1 1 2 7 2. These advanced bus clamping sequence just few moments back we have studied. So in sector 1 we first apply advanced bus clamping sequence 1 0 1 2 2 1 0 1, and for 30 degrees, for next 30 degree interval, we apply advanced bus clamping sequence 2721 -1212 1272. Okay, then we move from sector 1 to sector 2. We have to start with 2. So it will be 2 7 2 3 3 2 7 2. For next 30 degrees, it will be 3 0 3 2 3 0 3 2 2 3 0 3. Okay, then we move to sector 3. We have to start with 3 itself. 3 0 3 4 4 3 0 3. Then 4 4 7 4 3 3 4 7 4. Then 4 7 4 5 5 4 7 4. Then 5 0 5 4 4 5 0 5. Then 5 0 5 6 6505, then 6765, 5676, then 6761, 1676, and finally 1016 6101. Okay, so this is switching sequence in different sectors. Okay, so this double switching clamping sequence or advanced bus clamping sequence, it will result in clamping of a particular phase leg to positive DC bus for 60 degrees, then negative DC bus another 60 degrees, like that. I'm sorry here, what is this? This is okay. So this is advanced bus clamping switching sequence. Okay, it's very easy to write these numbers, like I have written here 2721, 2723. The rule is same, which I have told you which I have discussed with you in last many lectures when we were discussing advanced bus clamping PWM techniques. Okay, advanced bus clamping PWM techniques. Okay, so therefore it may result in 60-degree clamp. You can have 30-degree clamp PWM, or you can have split clamp PWM, continual clamp PWM. So this is one of the examples of advanced bus clamping PWM technique using new advanced bus clamping switching sequences like 1012, 2101 and 2721, 1272. Okay, which we had not discussed earlier. Now let us see the influence of these switching sequences on stator flux ripple and hence on torque ripple. Okay, let us use conventional switching sequence like 0127, 7210. So in alpha beta plane or in space vector plane, this is our alpha axis and this is beta axis. This is beta axis. So we have active vector 2 plus plus minus. We have null vector 0 minus minus minus, or null vector 7 plus plus plus. You already know. This is our reference vector. Say this is Vref, and this is this may be our alpha axis. This may be our active vector 1 plus minus minus. This is active vector 2. This is error voltage vector VR. When active vector, see, when null vector 0 is out, this is our required voltage vector along the load is Vref. When null voltage vector 0 is used, so this is what is required is Vref, but what we are applying at any instant of time is 0. So this is error voltage vector VR. When active vector 1 is applied, what is required is Vref, and what we are applying is V1. So error voltage vector is VR. When active vector 2 is applied, the required voltage vector is Vref, but applied voltage vector is 2. So this is error voltage vector VR. And when we integrate these error voltage vectors, this null voltage, error voltage vector, and this gives stator flux ripple, and along Q, D and Q axis, you already know this is your Q axis, this will be D axis. It gives something like this. First of all, we integrate this error voltage vector when null vector 0 is applied. So its integration will give us stator flux ripple when null vector 0 is applied, which will grow in this direction. It will have maximum values, negative values somewhere here. When active vector 1 is applied and this error voltage vector is integrated, okay, it will give us stator flux ripple, which will grow in this direction parallel to this. Okay, so this is when active vector 1 is applied. And when active vector 2 is applied, and we have error voltage vector VR, when it is integrated, it will give us stator flux ripple like this, which is moving parallel to this when active vector 2 is applied. Okay, and null vector 0 is applied for time interval tz by 2, active vector 1 is applied for time interval t1, active vector 2 is applied for time interval t2, and then null vector 7 is again applied. So this completes the subcycle. Now it is very interesting to see that as far as this d-axis is concerned, see, for example, this is d-axis. We will now talk not in terms of stator current, current ripple. We will talk in terms of, torque ripple. Our aim is not to reduce the THD of the current. Our aim is to reduce the torque ripple. So, for example, to make T6 torque, harmonic torque equal to 0 or T12 equal to 0 and so on. So, in terms of stator flux, you will see that along the d-axis, this is our dq plane. Along the d-axis, this is d-axis or this is d-axis, we will have fundamental stator flux. Fundamental stator flux. Fundamental stator flux psi1 is always aligned along d-axis. And along q-axis, what is aligned is stator flux ripple. So along q-axis we have stator flux ripple, which is responsible for producing torque, harmonic torques and hence torque ripple. So d-axis component is nothing but fundamental stator flux, and along q-axis we have harmonic fluxes, and those harmonic fluxes, and then this stator flux ripple along q-axis will give us nothing but harmonic torques and hence torque ripple. So therefore, if you want to reduce the torque ripple, the q component of stator flux ripple has to be reduced, not the d component, because along the d component you have fundamental stator flux, which is main flux, which is responsible for the development of torque in induction motor and set it into rotation. Whereas the harmonic fluxes are aligned along q-axis, and you have to reduce the magnitude of these harmonic fluxes. In other words, if you want to reduce the magnitude of harmonic fluxes, you have to reduce the magnitude of stator flux ripple along q-axis stator flux ripple. And if you are able to reduce q-axis stator flux ripple, you will be successful in reducing the magnitude of harmonic torques and hence reduce torque ripples. Okay, let us see how this can be done by various switching sequences. So first of all, I will see the comparison between, we will try to study the comparison between conventional switching sequence I should write conventional space vector based sequence and sine triangle sequence Now, if you see conventional space vector based sequence, okay, the conventional space vector based sequence, for example, if you consider sector 1, it is 0127-7210, and sine triangles PWM also gives same sequence 0127-7210, but there is one difference between the two. Conventional space vector based switching sequence or sine triangle switching sequence may be same, but the division of time between null vectors is not same in both. Conventional space vector based PWM gives equal distribution of null vector times between 0 and 7, whereas sine triangle PWM does not give equal distribution of null vector timings between the null vectors 7 and 0, and that results in more q-axis ripple as compared to conventional space vector based PWM technique. Let us try to understand that with the help of these diagrams. This is again our q-axis and this is d-axis. I am now considering space vector based sequence, which is 0127-7210. So first of all, null vector 0 is applied, so the stator flux ripple grows in this direction. When null vector 0 is applied, we already know, up to time interval tz by 2, so this is tz by 2. Then active vector 1 is applied for time interval t1. So active vector 1 is applied for time interval t1. Then active vector 2 is applied for time interval t2. Active vector 2 is applied for time interval t2, and then null vector 7 is applied for time interval tz by 2 again, and that it comes back to origin. So therefore your stator flux ripple, this is your stator flux ripple psi tilde, it moves along this triangle when 0, 1, 2, 7 sequence is used in a subcycle. In subcycle it moves like this. When null vector is applied, it moves along this line. When active vector 1 is applied, this stator flux ripple moves along this line. When active vector 2 is applied, it moves along this line. When null vector 7 is applied, it moves. So that completes the subcycle. It starts from origin, traces this triangular path, comes back to origin. And you can very interestingly see that the time interval between null vectors 0 and 7 is equal. So it is tz by 2 here, it is tz by 2 here also. So division of null vector time times is equal. So this is in conventional, I should write here, in conventional space vector based sequence. Or this is also true with triangle comparison PWM technique. Because I told you that conventional space vector based PWM can be implemented using triangle comparison also, in which case we have to add a common mode signal. This is our common mode signal, which is MCM equal to, if you remember, 0.5 M mid. If you are able to generate a common mode signal whose amplitude value is equal to 0.5 M mid and add that common mode signal to 3 sinusoidal modulating waves, we get our modified modulating waves, something like this. Phase R, phase Y, phase B, and compare that with high frequency triangular carrier wave, will generate the control pulses, and we will get same switching sequence as conventional space vector based PWM technique, and division of null vectors will be equal. That is, T0 will be exactly equal to T7. T0 will be exactly equal to T7 equal to Tz by 2 each. Okay, so this can be done by injection of common mode signal, or if you use space vector approach, in conventional space vector approach, automatically it does. And now you can see as far as d-axis ripple is concerned, this is along d-axis. I have already told you we have fundamental flux, so we are not bothered about d-axis. We are bothered about q-axis ripple. This is the q-axis ripple. This is the negative maximum negative q-axis ripple, and this is the maximum positive q-axis ripple. For conventional space vector based switching sequence or triangle comparison based switching sequence, where the common mode signal MCM equal to 0.5 M mid is added, okay, to 3 modulating waves. Okay, now if you use sine triangle sequence, for sine triangle sequence the situation is different. This is q axis, this is again d axis. Same switching sequence we will apply 0, 1, 2, 7. Now null vector 0 may be applied for a longer time period. Then active vector 1 is applied. You can see this is active vector 1. Then active vector 2 is applied. And then null vector 7 is applied. Now you can see very interestingly that this time interval T0 is not equal to time interval T7. That is, the division of null vector timings is not equal. So T0 in this case, you can say it is greater than T7, which means the null vector timings are not equal. T0 is not equal to T7 if you use sine triangle sequence, sine triangle PWM. Although switching sequence is same, but null vector timings are different. And this different null vector timing gives higher harmonic torque, because you can see, forget about d-axis, we are bothered about q-axis. You can see along the q-axis, since this null vector 0 is applied for a longer time period as compared to null vector 7, so negative maximum q-axis ripple increases. substantially. Increases substantially. Compare it with conventional space vector or triangle comparison based PWM. Here this is the negative maximum q-axis ripple, and here negative maximum q-axis ripple is much higher than this. And I already told you that this q-axis ripple basically represents the stator flux ripple. So stator flux ripple is more, which means it results in more harmonic torque. So harmonic torque will be higher, so therefore torque ripple will be higher. It will result in large torque ripple. So therefore, if you run your induction motor by conventional space vector PWM, technique, or by triangle comparison based PWM technique, you will see their torque ripple will be less. If you run the same induction motor using sine triangle PWM technique, okay, then you will see that torque ripple produced in induction motor will be more. Okay, so this is therefore conventional space vector PWM technique or triangle comparison based PWM technique is better than sine triangle PWM because of equal division of null vector timings, and of course that results in less negative maximum q-axis ripple, less torque ripple, whereas here negative maximum q-axis ripple is higher, so torque ripple is higher. Okay, in triangle comparison PWM technique, there is one third harmonic injection PWM. THI PWM means third harmonic injection PWM. If you use third harmonic injection PWM with k equal to 1 by 4, that will also result in equal null vector timings, that is T0 equal to T7, and that will also result in reduced q-axis ripple, q-axis flux ripple, and hence that will also result in reduced torque ripple. That is about third harmonic injection PWM, where also you have to inject a common mode signal like this with 3 sinusoidal waveforms, and your modulating waveforms get modified, and if you choose k equal to 1 by 4, it gives same harmonic spectrum as that, or same type of results as given by conventional space vector based PWM, and it divides the null vector timings equally, T0 equal to T7, and torque ripple produced is less. But the problem with this is that it will not give better utilization or best utilization of DC bus. Your inverter output voltage will not increase by 15.5%. It may increase by about 11 to 12% only. Whereas conventional space vector based PWM gives the reduced torque ripple, and it also increases the inverter output voltage by about 15.5% as compared to sine triangle PWM. Okay. Now let us see the comparison between double switching, conventional switching sequence and double switching sequence. We will now discuss stator flux ripple vector, and we will use these sequences: 0127, 7210, this is conventional, and 0121, 1210, this is double switching clamping sequence, that's advanced bus clamping sequence. Right, it will be very interesting to see that, for example, if this is your q-axis, this is d-axis. Now let us take 0127 switching sequence. In a subcycle, again null vector 0 is applied for time interval tz by 2, right? Active vector 1 is applied for time interval t1. Active vector 2 is applied for time interval t2, and null vector 7 is also applied for equal interval of time tz by 2. So this is the same thing which we have just few moments back discussed. Okay, so to put it in a more better way, null vector 0 active vector 1, active vector 2, and null vector 7. This is with conventional switching sequence, conventional space vector based switching sequence. 0127. Okay, I should write here CSV, conventional space vector, that is CSV based sequence. And now if you use advanced bus clamping sequence 0121, so this is my Q axis. 0 is first used, so let me show you. This is 0. It's used for full time interval T naught. Then 1 is used. 1 is used for less interval of time T1 by 2. 1. Then 2 is used. 2 is used for full time T2. Then 1 is again used. 1. So that completes this switching sequence. So ये आपकी D axis है. So I will again repeat 0, 1, 2, 1. Okay. इसमें आप देख सकते हैं Q axis ripple is higher than Q axis ripple produced by this, but D axis ripple has been reduced here because here active vector 1 is applied twice, and here it is applied for time interval Tz by 2 only, T1 by 2. Here it is applied for time T1. So D axis का अगर आप ripple देखेंगे, peak D axis ripple, it is more here than here. Okay, so that means peak D axis ripple is lower here. This is for advanced bus clamping sequence 0121. I should write advanced bus clamping sequence. So here I should write peak D axis ripple is lower, but Q axis ripple is higher. But I already told you that when we use this, okay, that was about clamping sequence 012. That does not apply here. So you can see D axis ripple is more here, D axis ripple is less here. Okay, now let us compare. I will write here stator flux ripple vector. We will use sequences, conventional space vector based sequence 0127 and advanced bus clamping sequence 1012. Okay, now again this is Q axis, this is my D axis, this is my D axis. If I use conventional space vector based sequence 0127, 0 is used, then active vector 1 is used, then active vector 2 is used, and null vector 7 is used. So T0 is equal to T7 in this case. Let me use now advanced bus clamping switching sequence 1012. Okay, this is again Q axis and this is D axis. I will use advanced bus clamping sequence 1012. So first of all, which switching sequence is used? 1 is used. It's used only for small interval of time T1 by 2. Then 0 is used. 0 is used for full time interval T0, so 0. Then 1 is again used. So when 1 is again used, it goes back. Okay, so 1 is again used, it's parallel to this, and then 2 is used. 2 is used for T2 time interval. So I repeat 1, 0, 1, 2. Okay, now you can very interestingly see, यहाँ पे अगर आप देखेंगे Q axis ripple इतना ज़्यादा है, because this is this is negative Q axis, then it becomes 0 here, it becomes positive, और फिर यहाँ कम हो जाती है, फिर से 0 हो जाती है. अगर यहाँ पे आप देखेंगे, this is peak of Q axis ripple, peak Q axis ripple. On the other hand, अगर यहाँ देखेंगे, peak Q axis ripple is much reduced. Peak Q axis ripple, it is much reduced in this case. So therefore, this advanced bus clamping sequence, which we have discussed today, just a few minutes back, it gives less Q-axis ripple, peak Q-axis ripple, than conventional space vector based PWM technique. So therefore, the advantage of this advanced bus clamping switching sequence 1012 is that it gives less Q-axis ripple and hence less torque ripple. So therefore, we have compared different switching sequences. We have compared conventional space vector based switching sequence with sine triangle PWM switching sequence, and we have seen conventional space vector based switching sequence gives less stator flux ripple and has less torque ripple. We have then compared conventional space vector based switching sequence 0127 with advanced bus clamping switching sequence 0121, and now we have compared conventional space vector based switching sequence 0127 with another advanced bus clamping switching sequence 1012. Okay, now we have found that some switching sequences give less stator flux ripple and hence less torque ripple, less harmonic torques, less torque ripple than other switching sequences. So based on this, we can now go for hybrid PWM techniques. Hybrid pulse width modulation techniques or hybrid PWM techniques or technique. So what we are doing is that let us take sector 1, this is your null vector 0, null vector 7, active vector 1, active vector 2, okay, our reference vector is somewhere here, maybe somewhere within this circle. Now it is found that if your reference vector is within this range, say यहाँ से यहाँ तक अगर आपका reference vector है, this is your reference vector, within this range, okay, here 012 switching sequence gives lower Q axis ripple and hence lower torque ripple. जबकि अगर आपका रेफरेंस वेक्टर यहाँ है, somewhere here 7 to 1, this is clamping sequence, this is also clamping sequence, gives lower torque ripple. Whereas if your reference vector is in between the two, somewhere here, then the conventional space vector based switching sequence 0121 gives lower torque ripple. Just recall what we have discussed when we were discussing various clamping sequences. If you remember, when we were discussing the clamping sequences, I will write here clamping sequences 012 and 721. This clamping sequence results in clamping of a particular phase leg to negative DC bus. This results in clamping to positive DC bus. Anyway, we have discussed these clamping sequences. And if you remember, I told you, we found there when we compared the two clamping sequences, we found that FQ, that is Q-axis stator flux ripple with clamping sequence 012 is less than the Q-axis stator flux ripple with clamping sequence 721 for alpha less than 30 degrees. And we also found that Q-axis stator flux ripple with clamping sequence 721 is less than Q-axis stator flux ripple with clamping sequence 012 for alpha greater than 30 degrees. This was the finding when we compared these two switching sequences in terms of stator flux ripples. And therefore, if your reference vector is within this period for alpha, this here alpha is less than 30 degrees. You can see alpha is less than 30 degrees. यहाँ से यहाँ तक, it's less than 30 degrees. And we know that for alpha less than 30 degrees, 0, 1, 2 clamping sequence gives less stator flux ripple. So that is what I have written here. 0, 1, 2 gives lower q-axis stator flux ripple and hence low torque ripple. On the other hand, if my reference vector is somewhere here where alpha is greater than 30 degrees, then 7 to 1 clamping sequence will give less stator flux ripple. That's what I have written here. 7 to 1 gives lower stator flux ripple and hence lower torque ripple. And in between two, this is the range of alpha, where conventional space vector based switching sequence 0, 1, 2, 7 gives lower torque ripple or lower stator flux ripple, which means lower torque ripple. So this gives us an idea that when our reference vector, when we synthesize a reference vector, we should not use only one switching sequence. We can use different switching sequences. For example, for alpha 0 to up to this, we can use 0, 1, 2 clamping sequence. For alpha within this range, we can use conventional space vector based switching sequence 0, 1, 2, 7. And for alpha within this range, we can use another clamping sequence 7 to 1, and these clamping sequences 0, 1, 2, 0, 1, 2, 7 and 7 to 1 within the given range of alpha will give lower stator flux ripples and hence lower torque ripple. So therefore we can use, this can be our what we call as hybrid PWM technique. In hybrid PWM technique, we use 0, 1, 2 clamping sequence, switching sequence first. For lower values of alpha, for medium values of alpha, we use 0, 1, 2, 7 switching sequence, which is conventional space vector based switching sequence for medium values of alpha. And for high values of alpha, we use clamping switching sequence 7 to 1. So this is nothing but hybrid PWM technique. This is called hybrid PWM technique. Why is it called hybrid PWM technique? Because it is the combination of different PWM techniques. For lower values of alpha, it uses bus clamping technique 0, 1 with switching sequence 0, 1, 2. For medium values of alpha, then as your alpha goes through medium values, your reference vector goes through medium values of alpha, it uses conventional space vector based switching, conventional space vector PWM, that is switching sequence 0, 1, 2, 7. And when your reference vector is going through high values of alpha, it uses bus clamping sequence, bus clamping PWM technique with clamping sequence 7 to 1. And this is in order to give lower torque ripple. The aim is to produce lower torque ripple in the induction motor drive. So this is the concept of hybrid PWM technique. And another combination may be like this. Another combination may be 1, 0, maybe 1, 0, 1, 2, 0, 1, 2, 7, 2, 7, 2, 1. If you use advanced bus clamping technique, in advanced bus clamping technique, this is null vector 0 or null vector 7, active vector 1, active vector 2. So this is the range. That means if your reference vector is within this range of alpha, then use double switching clamping sequence or advanced bus clamping sequence 1, 0, 1, 2. For medium range of alpha, if your reference vector is VREF is within this medium, use conventional space vector based switching sequence 0, 1, 2, 7. And for high values of alpha, use advanced bus clamping sequence 2, 7, 2, 1. So therefore for lower alpha, we use advanced bus clamping switching sequence and hence advanced bus clamping PWM 1, 0, 1, 2. For medium values of alpha, when our reference vector is going through this region, we use conventional space vector PWM technique with the switching sequence 0, 1, 2, 7. And for higher values of alpha, when your reference vector is having higher values of alpha, it is somewhere here close to active vector 2, we use advanced bus clamping PWM technique again with switching sequence 2, 7, 2, 1. So this is another example of hybrid PWM technique. Just few moments back, we have compared 0127 with 1012. For lower values of alpha, 1012 gives lower stator flux ripple and hence lower torque ripple. For medium values, conventional space vector based switching sequence 0127 gives lower stator flux ripple, q-axis stator flux ripple, and hence lower torque ripple. And for high values of alpha, the advanced bus clamping sequence 2721 gives lower stator flux ripple, q-axis stator flux ripple, and hence lower torque ripple. So this is how you can combine various switching sequences which belong to different PWM techniques and which gives rise to hybrid PWM technique for reducing torque ripple. So this will give lower torque ripple in induction motor. So the hybrid PWM techniques have not been fully explored by researchers. You will not find much literature available in the hybrid PWM techniques. Much more needs to be explored. More research work needs to be done in this area for the implementation of hybrid PWM techniques in order to reduce the torque ripple, okay, in induction motor drivers. So I advise you, my dear students, some of you can, take your projects and dissertations and work on this area. This is a fairly new area. Not much work has been reported. And you can have some very good publications if you produce some good results. If you use this hybrid PWM technique using advanced bus clamping switching sequences, conventional switching sequences, and so on. And if you are able to give good results with lower torque ripple, you can have very good publications. So this is that's all about my today's lecture, and I would advise you to go through some of the very good papers. So yeah, these are some of the references. I hope these are visible to you. One of the very good publications is from SDT Robertson and KM Haber. The title of the publication is Torque Pulsations in Induction Motors with Inverter Drives. It is published in IEEE Transactions on Industrial and General Applications, Volume 1GA. It's way back in 1971. See, in 1971, already some preliminary work was done. Okay, and then another publication is by B.T. Ranganathan, Lecture Notes on Electric Drives, Department of Electrical Engineering, Indian Institute of Science, IISc, Bangalore, 2006. And then there is a book written by R. Krishnan, Electric Motor Drives. You can refer to this book also. And for this torque ripple reduction and stator flux ripple reduction, you can refer to these publications, G. Narayanan and V.T. Ranganathan. The publication is Analytical Evaluation of Harmonic Distortion in PWM AC Drives using the Notion of Stator Flux Ripple, IEEE Transactions on Power Electronics. It was published in March 2005. Another publication is AC Binoj Kumar, J.S.S. Prasad and G. Narayanan, Experimental Investigations on the Influence of Inverter Switching Sequence on Motor Acoustic Noise, IEEE Transactions on Industrial Electronics. It was published in February 2013. Please go through these references, try to download these references, and you will get more information about stator flux ripple reduction, torque ripple reduction using different hybrid PWM techniques. So that's all about, I declare the end of this lecture series on, this flux ripple, current ripple reduction and torque ripple reduction. We started with analysis of stator flux ripple, and we in fact first produced the error voltage vectors. We integrated those error voltage vectors produced through the diagrams, through the graphs on DQ axis stator flux ripple vector, and then we we divided that into two components, D axis component, Q axis component. Then we have gone through the rigorous mathematical evaluation. We found how we can find the RMS value of D axis ripple, RMS value of Q axis ripple, okay, by taking the square and then mean square and then square root of mean square, that's RMS value. And we have seen how this stator flux ripple is dependent on three parameters: alpha, Vref, alpha, and TS. And Then we tried to study the influence of different switching sequences on stator flux ripple, of course, d-axis and q-axis stator flux ripples, and we have seen that 60-degree clamp PWM gives highest stator flux ripple or highest THD in the current, whereas 30-degree clamp PWM technique gives lowest stator flux ripple or lowest THD in the motor winding current. And over last couple of lectures, we have been discussing about torque ripple. First of all, we learned about what are the causes of torque ripple. We found that the interaction of stator fundamental flux and rotor harmonic currents results in strong torque, harmonic torques, and torque pulsations or torque ripples. And in today's lecture, we try to see how we can use low switching frequency PWM like selective harmonic, elimination of torque, and how we can design our PWM strategy, how we can calculate switching angles in order to eliminate certain specified torque ripples, like make T6 equal to 0 or T12 equal to 0, T18 equal to 0. And we have seen how we can use high switching frequency PWM techniques for reduction of torque ripples. We have seen some advanced bus clamping switching sequences, and we have compared various switching sequences from the point of view of reduction in q-axis stator flux ripple and hence reduction in torque ripple. And finally, we have ended up with hybrid PWM techniques. We found that in a particular sector, when our rotating reference vector is rotating in different sectors, for certain range of alpha, you can use one switching sequence. That means one type of PWM technique. For some other range of alpha, use some other PWM technique or some other switching sequence. And for some other range or higher range of alpha, use a different PWM technique or different switching sequence in order to give reduced torque ripple in induction motor drives. And this gives rise to a very interesting topic on hybrid PWM techniques. In hybrid PWM techniques, basically, we use the combination of different PWM techniques or different switching sequences depending upon the range of spatial angle alpha. The aim is to reduce the stator flux, q-axis stator flux ripple, and hence torque ripple. So with this, I end my today's lecture and the lecture series, about 4 to 5 lectures on stator flux ripple and current ripple and torque ripple, how they are produced, how they can be reduced using different switching sequences. So please go through this lecture, and in case of any doubts, put your queries on WhatsApp and stay connected. So I wish all the best to all of you. Thank you.